Okay, I am going to do a video key for test 1 for my OChem 2 students. So for this, I'm just going to go through every question and talk about how I would recommend that you solve the question, or like how I would approach the question. And then if you have any questions after you've gone through the exam, just let me know and we can talk through them. So the first question is, which Grignard reaction shown could be used to prepare the alcohol shown? So how can we make this happen? And a fast way to do this is with a little bit of retrosynthesis. If you think about the fact that usually ketones with some nucleophile that looks like this, like ketones usually will make an alcohol. If a Grignard attacks like this, we have gotten alcohol that way a few times. So I'm looking for something like that. Or it could go the other way where this part is already there and then the Grignard looks like this. So those would be the two things I would probably be looking for. So actually the Grignard, let's see, it would have to have, yeah, just one carbon off of it and then MGBR. Okay. So that's what I'm looking for. So right off the bat, I know that this one won't work because this alcohol is acidic. But both of these, so if it's acidic and we have a carbon ion that's really strongly negative with alcohol of any kind, it will just do an acid-base reaction and you will get this plus OH minus. Both of the next two look like good options for me though, so I'm just going to double check and see. If this attacked here and this went up, I would get O minus. And then this lone pair is what made this bond. It's just to make sure that my number of carbons is right. And if you're not sure, you can count. So it's a 6-membered ring plus 1, 2, 3, 4. And then off of 3, there's a methyl. So 1, 2, 3, 4. And off of 3, there's a methyl. So that looks right. So I'm going to say that's definitely an option. And then same thing over here. This looks like the one I already drew, but this would attack here and kick up. And so we'd get O minus, and then these electrons form a new bond. And then our 1 carbon, and then, okay. So both of these look right to me, so I'm going to go with answer choice D. Sorry for my voice. My husband got me sick over the weekend, so. Okay, next question. How many signals would you expect in the NMR spectrum of the compound shown below? So first thing I notice is that there's symmetry. And so you can kind of cut this in half and know that these are going to be identical. So I'm only looking at half of this molecule. So I know that there's 2 hydrogens here, 2 hydrogens here. There's no hydrogens there because there's already 4 things bonded to this carbon. And then 3 hydrogens here. So I'm seeing 1, 2, 3 signals, and that's how many there would be. Now, the integral, so answer to this is A, but just to take it a step further, the integral for each one of these would be equal to 2, 2, and 3, but that is if you multiplied all that by 2, because it's double, you'd get 4, 4, and 6 for the integral, so either of those would be valid integrals. So that's what I was looking for that one. I don't know why my app kind of got rid of this, but it's just an arrow that goes from this to this. So when reducing a carbonyl, when a reduction to a carbonyl group occurs, so we've seen a carbonyl group, oops, that shouldn't be negative, with a hydride, make a reduction, we get O minus. The carbon, so that's a reduction. When a reduction to the carbonyl occurs, the carbon attacked undergoes this hybridization change. So I had a very similar question to this. It might have just been the reverse of this on the practice exam. So I had anticipated y'all to get this pretty easily, but the hybridization of this one is sp2, and the hybridization of this one is sp3. So that is the change from sp2 to sp3. So that is answer choice A. And if you just know that it starts out as sp2, you could eliminate B, C, and D and have it narrowed down that way. Or if you just know that it ends up as sp3, that would eliminate B, D, and E. So that's what I mean when I say use what you know to eliminate right answers, is just take the information you know to try to process through. Okay, aldehydes are more reactive than esters, which best explains why. So first I'm just going to look for true statements. The carbonyl group of the aldehyde is more sterically hindered than the ester. Well, if I'm thinking about an aldehyde versus an ester, definitely this group on the ester has more steric hindrance. So that's not true. So I'm going to eliminate that just on the first sentence. This one says the carbonyl group of the aldehyde is more sterically hindered. Again, that's not true. I'm eliminating that based on the first sentence. This one says the carbonyl group of the aldehyde is less sterically hindered than the ester. So that's true. And just quickly, I'm going to say that D says the same thing. So those things are true. So then the next thing is the carbonyl carbon of the aldehyde is more electrophilic. That's true. It is more electrophilic, so that's true. The carbonyl carbon of the aldehyde is more electrophilic, true. So then we're only looking at this last sentence. Due to the additional resonance structure present in the ester. Well, we know the additional resonance structure present goes up like that. And that makes this oxygen positive. So there's another resonance structure where the carbon is neutral. So because of that, this is true. But just to double check, I'm going to read this one. Due to the electronegativity of the oxygen in the ester. Well, the oxygen in the ester is actually pulling electron density away, right? So that leaves a partial positive there. Now, we talked about that a few times in class. I don't know why I made this negative. We talked about this a few times in class. So hopefully you got that right. But if you didn't and you picked answer choice D instead, you actually got lucky because the answer key was initially wrong. And so we gave it to you if you got C or D. Okay. This next one, select the structure of the major product in the following reaction. More than half the class got this wrong, which I'm surprised by. Normally students don't really struggle with this. So I think I want to show you the mechanism to clear it up for you. But first I'll show you how I would approach this. So when I see KMNO4 and it's hot, I know that it's going to cleave a double bond and add an oxygen on each side. So that would give me this. And it would just give you 2 of these. And we've done a question exactly like that. I don't remember if it was in recitation or what. Maybe it was in PLTL, but I know there was a question exactly like this. It may not have been these exact structures, but it gave you 2 of the same thing. Maybe it was in your homework, but somebody asked me about it. So I know that you've seen one like this before. And I think a lot of people got hung up on the acid, but that is just a part of the mechanism. And we haven't talked about it a ton, but I think its biggest role is to, like as a workup, to get everything back to normal. But I'm going to show you sort of what happens with oxidative cleavage. So if you have K, the K is the counterion. So if you have MnO4, it looks something like this. And because this manganese has d orbitals, it's able to have more bonds than oxygen normally would. And so basically the oxygen double bond will attack here, and then this will back attack, I think. And then the oxygen here bonds on this side. I think. Those arrows don't look right to me. Sorry, I should have pulled this up beforehand. Well, my brain's blanking, and I don't want to tell you wrong. There is a version of this in your notes. It's with the oxidative cleavage of O3 instead. I bet, you know what? I bet I could pull that up right now. I bet I have your notes on here for this. Let's see. This was your notes for chapter 12. Here's your redox notes. So if you go to, let's see. Is this it? I thought I included it, but maybe it was from your notes from a previous semester. Anyway, you should be able to look up that mechanism if you're curious about it. I think it makes like a nice circle, but you didn't need to know the mechanism. Oh wait, that's not where I'm trying to be. Sorry. You didn't need the note to know the mechanism to be able to answer this multiple choice question. All you needed to be able to do was to know the end products. And I wonder if this acid is what threw you off, but even if you weren't sure about the acid, you knew that KMNO4 hot cleaved that double bond and adds an oxygen to either side. But so for some reason, and maybe y'all can give me some insight into it, more than half the class got this wrong. So even though you'd seen a question like this, I basically use this as one of your drop questions. So we just, instead of it being out of, normally I do 15 out of 14 to give you a bonus, but this time I did 15 out of, I think I did 15 out of 12. And this was one of the reasons, this was one of the questions I dropped it on. So I'm not sure what it is about this one that got y'all kind of mixed up, but maybe it is the mechanism. But I'm pretty sure what happens is basically like this oxygen will attack here, and then this thing back attacks over here, and it makes sort of like a bond with both of these. We'll see a similar mechanism to this later, but it sort of looks like a square. And then these bonds basically break, and that's how we end up with the two double bonds to oxygen, I think is how it happens. But yeah, so I'd be curious why, if anyone could give insight into that, why that one was considered a difficult one. Okay, the next one, what is the predicted product of the reaction shown? So ozone would do the same sort of oxidative cleavage thing, and more than half the class didn't get this one wrong. So it's just something about KMNO4 that I'm surprised by. Maybe it's because you thought, oh, if there's aldehyde, it'll keep oxidizing, but I don't know. Okay, so this one, ketone and hydrogen, O3 and DMS, and DMS is basically just the solvent for that first reaction. And then this second one is an oxidizing agent. It's Jones reagent, so it will take an aldehyde to a carboxylic acid. So that will be our final product. So what I'm looking for to eliminate answers quickly is, I know that's wrong because we cleaved that double bond. So it has to be 2, 4, or 5 just right away. I know both sides did not turn into carboxylic acid, so that's wrong. And I know the one aldehyde turned into a carboxylic acid, so that's wrong. So answer choice 2 is the right answer here. Okay, next question. Which of the following best represents the predicted approximate chemical shift in coupling for hydrogens? Okay, so this one, something that I think happened is we talked about finding ranges, but I guess, well, first I'll say how I would approach this is I know that this is, there's a strong dipole moment here because oxygen is electronegative, but also because there's a resonance structure. So this is strongly partial positive, which means it's pulling on the electrons around it. So before I can determine what the chemical shift of this is going to be, I'm going to say the chemical shift is likely in the 1 to 2 range. And I know it's in the 1 to 2 range because if I go to my table right here, the NMR shift table, methyl CH3s, they're like around 1. Methylene is CH2, that's around 1.2. If it has more electron density, more carbons around it, it'd be 1.7. And then if it's 1 away from a double bond, it's 2. So typically, these hydrogens that are on fully saturated carbons are anywhere from 0.9 to 2. But we know that as things are more next to more electron withdrawing groups, they start to shift over, right? So they're more de-shielded the more they shift. And a good example of that is if there's a hydrogen attached to a carbon next to an alkyl halide, that has electron density pulling it away, which means that hydrogen is more de-shielded. So I think that this chemical shift of these carbons here and here is probably going to be in the 1 to 2 range, but those two in green are going to be closer to 2. And then this one, this CH3, I think would be at the end. I'll do it in this color. This would still be in the 1 to 2 range, but it's going to be closer to 1. That would be my thought process when I'm going through this. And we even did a very similar example to this in our PLTL, where it was a structure, something like that. And then we had a hydrogen over here, and you had to identify the chemical shift for that. So you've seen examples like this before. And so when I say that I don't want you to be able to just memorize the chart, but I want you to be able to look at the chart and think about, okay, what does this mean? This is the example I'm giving you. These charts don't have every single case possible on there. These charts give you a general range, and then you have to be able to think within those. So I'm thinking that this is going to be likely in the 1 to 2 range. It could even, for these that are pretty electronegative or next to something pretty electron dying, like that strong partial positive, it could even go all the way to 3. But these greens, I'm going to tell you what, they're not going to be at 1 because that's a perfectly shielded hydrogen. So that's the first thing I'm thinking. So I'm eliminating 1. And then all these 2 or 3, I'm like, oh, those are fair game. So the next thing I look at is the chemical shifts. So if we have our structure, it's not the chemical shift, the splitting. For each one of these, this right here, the integral would be equal to 3. It didn't ask that, but it's useful to have. And then it's splitting. How many neighbors does it have? Well, if I look at it, the adjacent carbon, that carbon has no hydrogen, so its neighbors is 0, so it would be a singlet. It didn't ask me, but I'll go ahead and do the rest of them. If I'm looking at this one, the integral would be equal to 2. Its neighbors, it has 3, so that would be a 3 plus 1, so that would be a quartet. And then this one right here, it would integrate to 3. It has 2 neighbors, so n equals 2, so 2 plus 1 equals 3. So it would be a triplet. But it's not asking about all of them. It's only about asking about this one over here. So it's definitely a singlet. So I'm going to get rid of anything that does not say singlet. So that leaves it down to B or C. I accepted B or C as an answer choice because I wanted you to be able to show that you were thinking critically. about this and not just saying like, oh, the first hydrogen I see is next to a methyl is at 0.9, so that's probably right. So I did not accept A as an answer choice, but this is another one where I justified dropping it down from 15 out of 14, and then the KMNO4, I made it 15 out of 13. Sorry. Yeah, and then this one, I was like, all right, we can make it 15 out of 12. I'll go ahead and drop that one too. So I accepted both answer choices, and I also dropped an extra question. Okay, this next one, the NMR signal for which of the indicated protons will occur at the lowest frequency or the most shielded signal. So you can look at your chart for this, obviously. This OH, we're going to look for hydrogen off of a carboxylic acid. These three are going to be off of an aromatic ring. And this one is going to be very similar to what we had before. It's going to be in the 1 to 2 range, probably closer to 2. We've already looked at that, but I'm going to look at the aromatic ring and the carboxylic, and the carboxylic acid. So let's see, aromatic ring. I see 2 aromatic rings, one here and one here. The one down here is a hydrogen directly bonded to it, which is what we had in our case, so 6.5 to 8 for that. And then the hydrogen off of a carboxylic acid right here is around 12. So if my options are, I'm going to scroll back up. If my options are 12 and 6.5 to 8, then this one right here is probably going to be the best one. It's going to be the lowest frequency or the most shielded. Okay, let's see. Example, and this one actually would be if you want to just take one more thing into account, because there's a lone pair here that can make an additional resonance structure for this ester where the carbon is not positive, but this oxygen is. I would say this one would probably be closer to 2. Like maybe a little bit like lower on the 2 side and not near 3 the way that the one above might have been. Okay, next question. Which of the alkene groups shown produces stronger signal in an IR spectrum? Well, one, there's a mistake. This second should have said fluorine. Okay, so the first questions that I ask when I look at these is I'm looking for true statements, and I'm also looking for accurate explanations. So when this question says, which of these shown produces a stronger signal in an IR spectrum, I'm thinking stronger signal equals more polar. And we did a whole quiz question on this, so hopefully you got it from that. So I'm looking for the more polar bond. And just from looking at these, I know that fluorine is more electronegative than chlorine. So this is probably going to be more polar. That's just my first thought when I saw this question. That was the first thing I thought. Now I'm going to read these statements. Compound 1 produces a stronger signal because fluorine is more electronegative than chlorine and produces a larger dipole moment. So that is a good guess for me. Compound 2 produces stronger signal because chlorine is more electronegative than fluorine and produces a larger dipole moment. Even if I don't know about the dipole moment thing, you can eliminate this one because chlorine is not more electronegative than fluorine. So you know that's wrong. The alkene groups produce similar signals because their structures are so similar. Well, their structures are similar, but we know that the intensity of the signal is equivalent to the polarity, so that's not right. And then the alkene groups produce similar signals because both have vanillic halogen atoms. So that's true. They both have vanillic halogen, but still, if we have something that is going to make one bond more polar than the other, it's going to be more intense than the other. So, and I figured you'd be able to reason that. So we talk a lot about fluorine being the most electronegative element, and we had that quiz question about polarity. So I had hoped that would be pretty straightforward for you. Okay, what is the structure of the compound the following NMR spectrum? I don't know why this happens, but they don't always show up on my... they don't always show up in this app, but they do show up in the original one. Okay, so we have a peak at 1. Okay. So we have a peak here. We have a bunch of peaks here. Oh, this tells me singlet, multiplet, triplet, and triplet. Okay. So immediately when I see a peak in the 12 region, I think that this is going to be a carboxylic acid. And that's something I think because I guess I haven't memorized these, but just when you see it so often, you recognize that. So, and a lot of times really I'll sort of draw a line around 4 or 5 because 6 to 8 is usually going to be aromatic or one away from a double bond. Hydrogen that's on a carbon, one away from a double bond, so resonance basically. And then I also usually recognize that aldehydes occur at 10, and then carboxylic acids occur around 12. So above 4, you can get some really characteristic shifts, and I kind of look for those first. So based on that 12 peak alone, I know that A is wrong because that's an aldehyde and not a carboxylic acid. And if you don't know that CHO off the top of your head is an aldehyde, where carboxylic acid is CO2H, that's something that we talked about in chapter 2 with functional groups, and there's something you should just kind of recognize. So I immediately eliminated one answer just for looking at that peak at 12. And now I'm looking at these, the peak at 6 to 8, and I'm thinking that's probably an aromatic ring. It has 5 hydrogens on it, so I can get rid of B because there's no aromatic ring there. And then I see that C, D, and E are aromatic rings. And they have 1, 2, I'm going to just draw dashes here for hydrogens. So these are not methyls, those are just me counting hydrogens. 1, 2, 3, 4, 5 hydrogens. So C is an option. 1, 2, 3, 4. So only 4 hydrogens in the aromatic region on this one, so that can't work. And then 1, 2, 3, 4, 5. Okay, so just from knowing that this peak right here is in the carboxylic acid region, and these 5 hydrogens are in the aromatic region, I can eliminate every answer choice except C and D. So just like that, I've eliminated everything but C and D. And now the next thing I would do is, okay, all my peaks are accounted for except for these 2 on this one and these 2 on this one. So what are those peaks going to be? So I would say on this one we have 2 peaks. The integral for them would be each equal to 2 because there's 2 hydrogens. Integral is equal to 2 for each of them. They are probably going to be in the 1 to 2 range, but they're going to be shifted over, probably. Shifted to the left because they're next to that carboxylic acid. And then the splitting pattern is this one right here. On the left, it has 2 neighbors. So the split is going to be 2 neighbors plus 1. And then the one on the right also has 2 neighbors plus 1. So these are both going to be triplets. So 2 that integrate to 2 that are both triplets, well, we have that. So that is probably our answer, but just to check, let's come down here. So this hydrogen, there's just 1 here. This hydrogen, there's 3 in this region. So we have 2 peaks. One is going to be integrate to 1, and the other is going to integrate to 3. And we don't have that, so we can eliminate that. But also just double checking, this one that integrates to 1 is going to be a quartet. And this one that integrates to 3 is going to be a, I wanted to say duet, but what's that called? Singlet doublet. So I don't have that pattern, so I know that that's not right. So I am eliminating that one as well. So that's kind of the process that I go through whenever I'm trying to solve spectroscopy questions. And I think something that I didn't put together is like, for me, I have that process pretty consistently. Other people maybe are taking longer. And so I think that's something that I didn't realize how long some of these questions were going to be. And so that's why I accepted multiple answers on some of them, but also that's why I dropped so many. Okay. How can you distinguish between cyclohexanol and cyclohexane carboxylic acid using IR spectroscopy? So this is another one I accepted multiple answers on. The first thing I'm looking at when I'm looking at functional groups is I'm thinking like this is an alcohol. This is a carboxylic acid. The only other key peaks that are present usually is CH. Those are usually somewhere above 3,500. But we don't care about single bonds between carbons or anything like that. So that's the only thing we care about is what I have circled and the carbon-hydrogen bonds. And so between these two peaks, the biggest thing is this carbon-oxygen double bond is going to appear. So if I'm looking at the difference between the alcohol and the carboxylic acid, a carbonyl is going to appear. But also typically alcohols have low broad peaks. Carboxylic acids usually have lower broad peaks due to the intensity of that signal, or of that bond, the polarity of that bond. And usually the carbon-hydrogen bonds, like in a carboxylic acid, kind of come down like that. So those are the kind of two things I'm looking at. Is it's going to be like a broader, it's going to be that characteristic shape of carboxylic acid. But then the other thing is I'm looking for this C double bond O. So so I'm going to just start looking for true statements. The carboxylic acid shows a broader alcohol absorption compared to the narrower OH, so that I'm going to put maybe. That could be an option. Cyclohexanol shows a carboxylic acid not present. So, cyclohexanol shows a carbonyl. Cyclohexanol doesn't have a carbonyl in it, so we can eliminate that. Carboxylic acid shows a carbonyl that is not present in cyclohexanol. That's a good choice. Both of those are good options. D is definitely wrong. You can tell them apart because of the carbonyl. And E is more than one of these choices. So answer choices I accepted was if you just got C, and if you just got E, I accepted it. A is, it is true that this shape changes. But the shape changes can't be the only thing you picked up on, because you should have known that this big change was going to happen. And if you just stopped when you found the first answer because it was mostly true, that's a bad test-taking technique. So be sure to read all the questions going forward. Okay, this question, determine whether each of the IR spectra given is consistent with the structure of an alcohol, a ketone, an aldehyde, whatever. So the first thing I'm noticing is we have a broad spectrum down here. So this is probably going to have some kind of hydrogen bonding. On this one, I'm noticing the carbonyl peak is usually in that range. Or it could be, it's hard to tell the wave number, so it could be a CC or CO. So those are the things I'm looking for. This is probably alcohol. I feel like this is typically what an alcohol peak looks like based on the shape, and the shift looks to be like around 3,600, 3,600. Okay. Spectrum 1 is consistent with an aldehyde, and spectrum 2 is consistent with an alcohol. I think that's true. Spectrum 2 is consistent with an aldehyde. I don't see that being true because there's no big super deep peak right around here. So I'm going to say no, that's probably not true, based just on the absence of the carbonyl peak. Spectrum 1 is consistent with a primary amine, and spectrum 2 is consistent with a secondary amine. Spectrum 2 has some hydrogen bonding, H with FON. Spectrum 1, though, doesn't. And so just based on spectrum 1 not having that, I'm eliminating this one. Spectrum 1 consistent with a ketone, and spectrum 2 consistent with a carboxylic acid. Okay, maybe. And I believe I took both answers on this one, A or D. Hopefully. I think I told Jesse to do that. Because I could see you getting kind of caught up in that. But I can double check. And then E, spectrum 1 is consistent with carboxylic acid, and spectrum 2 is consistent with a primary amine. So 1 could be consistent with this part of the carboxylic acid, but we don't see the broad peak that comes from a carboxylic acid over there. So I think that is why that one would be wrong. And hopefully you know that too with 2, that this one would not be right because that's not what carboxylic acids usually look like. But I could see your reasoning for that, so A or D I accepted, even though D wouldn't be right. I think. Let me make sure that I told Jesse to do that. Oh, no, I forgot to. Okay. I will, I'll go back and look over your grades and add, if you got D for that question, I'll add a point. Okay. And then the last one, 13. Oh, no, this isn't the last one. We have a few more. For the given reaction, which of the following changes in the IR spectrum is consistent with this occurring? So this one's going to disappear for sure, and this one's going to show up for sure. That's what I'm looking for. So let me go double check the absorption. I think that one's around 720, but I'll look. The carbonyl absorption, C double bond O. Yeah, it's 1680 to 1750 is going to go away. And then let's see. We'd expect to see one at 3300 appear. And we'd expect to see one at 2100 appear. So that's what I'm looking for. So when I go back to this, I'm looking for one in the 1700 range to disappear. So this one's a little too high for that one appearing. It's like usually around 1700. This is a good option. This seems a little bit high to me. It's usually 1650, so I don't know about that. What were my numbers? Let's see. 2100 for the carbon double bond. 1680. Okay, so 1680 to 1750 is going away. So this one's not in that range. This one's not in that range. This one's close, but I would say unlikely. I'll put a little tilde by it. And then absorption at this one would disappear. So if you just knew that this one was gonna, that was gonna disappear, you should be able to narrow it down to B. But just in case, we'll see if this one was around 3300 and this one was around 2000. And that is both present here, this one and this one. So if you just knew that the carbonyl was going to disappear, you should have been able to get this question right. Okay, that one for some reason is not showing up. Let me go look at what that question was. Okay, so the question is, we're going from this to this. Right, hopefully. Not quite. I missed a methyl group. Oops, I clicked on the wrong one. For the following conversion, has the starting material been oxidized, reduced, or a combination of or neither? So this group went from OH to O, so this has more bonds to oxygen. So oxygen bonds increase, so that's oxidation. And this is one of the questions I mean that like when you go through, that's like a quicker and easier one. So I'm working this in order just to help you guys, but if it were me and I was going through the test, I would have first started by being like, oh, I have to do a bunch of reactions on this, so I'm going to skip this one. I could do this one pretty quickly, so I probably would have done 2 and then 3. This one, 4, the words would have gotten caught up on, so I probably would have skipped that. 5, I could have done quickly, so I would have done that. 6, I probably would have skipped. 7, I probably would have skipped. 8, I could do pretty quickly, so I probably would have done that. And 9, 10, I probably would have skipped. 11, I probably would have done, because I think I could have done that, but maybe not. I would have skipped 12. It would have been intimidating. 13 I could have done pretty quickly, and 14 I could have done pretty quickly. And then I would have gone back through and done the ones that are multi-step. So I'd go back through and be like, okay, of these, which ones can I do? They just take longer. So like the first one, I could do, that one takes longer. And I already would have done 2 and 3. 4, I would have tried to eliminate just what I could and sat down and really tried to read it and see if I could make sense of it. 6, I would have probably done on that one. 7, I could see myself getting stuck between 2 and coming back to it. 10, I would have done on the second pass through. I would have done 12, I would have done on the second pass through. I might have saved that one for later because there was 2 spectra, so that would have been intimidating. And then I would have done 15. So that's what I mean when you should go through, collect points. And I would have done all these and just the quick ones, the first pass through, then do the free response, and then come back for the multiple choice you're not sure on, because the free response is worth more points than the multiple choice. And the way I kind of break down your test is it's 15 multiple choice and then basically a quiz equivalent. So the goal is for you to take about 20 minutes on the quiz, maybe 25. That's what you normally do on a quiz length thing. And then the other 25 minutes to be on the multiple choice. So I'm anticipating you spending 25 to 30 minutes on this. So that would be 2 minutes per question. So my goal is that you're able to get through the questions relatively quickly. And I think a lot of people ran out of time because spectrum questions are longer. So that's good for me to know. But also that's good for you to know for the future is it's not enough to just understand the concepts, but also you should be thinking through what's the best, thinking through, like, am I going fast enough? Do I understand the concepts quickly that I can quickly get through this, or do I just kind of understand them and I'm struggling my way through every time? Okay, my throat is hurting for how much I'm talking, so let me get to this last one. Oh, this is a long one, and for some reason it's not showing up on here. Okay, how many carbons are in that structure? 1, 2, 3, 4, 5, 6, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And then BR, and then there's, I think, one here and here. Okay. MgBr. Oh, wait, no. Magnesium and ether. And then aldehyde and water. Okay. So the first thing I know is this is going to become MgBr, and so then basically this whole thing goes away, and this is a lone pair. And so now this will attack, and this bond will go up. I'm actually going to draw this one in a different color, just because I think it'll be easier to see. And I'll draw this lone pair. I don't like the light blue. I'll draw this lone pair in, that one's hard to see too, orange. So, 1, 2, 3, 4, 5. And then a new bond formed here from this lone pair. This oxygen came up. And the hydrogen's still here. It's implied, so we don't have to draw it in. And then if we add water to that, acid would be better, but basically that would get taken, and then we would have, you don't have to redraw it all out. Sometimes on multiple choice I kind of just draw the hydrogen in right there just to save time. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogen or carbons. So 1, 2, 3, 4, 5, 6. Wrong. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9 contender. 1, 2, 3, 4, 5, 6, 7. Wrong. Double bond, where did that even come from? That's crazy. 1, 2, 3, 4, 5, 6, no, 5, 6, 7. Well, we need 9, so that's wrong. So, boom. Okay, that's great. What's excellent about this is, yeah, if you know that Grignard reagents will react with ketones to form alcohols, well, one, you can immediately eliminate this because the double bond magically comes from nowhere. You can also really eliminate, if you just know, like, these two things are going to bond together. So the total thing has to have, even if you didn't know it was a chain, it had to have gained carbons. And this one, I don't even know if it did gain enough carbons because 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It gained 1 carbon. No, it didn't because it started with 6 on this chain. 6 with then 7, 8. So this had 6, 7, 8. So it just rearranged its carbons. It didn't gain any. That doesn't make any sense. This one, I think, did gain carbons. So you'd have to know between these two. But if you just knew, like, oh, I should end up with more carbons than I started with, you could automatically eliminate 1, 3, and then the double bond should have been suspicious that you got rid of 4. So you would have really only been deciding between 2 and 5. And that's what I mean for use what you know to eliminate wrong answers. So that would be answer choice B. Okay, I hope that that was helpful and some of those test taking techniques helped you. I'll go back and make sure that I accepted A or D for answer choice 12. And then let me know if you have any questions. Okay, I won't see you in class tomorrow because I am doing class remotely, but it is going to be synchronous, so I'll see you online at our normal class time. Okay, bye.